I'm going to go a little bit out of order. So electrodynamics is the title of this chapter. Electrodynamics means the study of flowing electric current. The flowing of electric current is electricity. So to give you the definition here, electricity, the continuous flow of electrons along the surface of a conductor. Recall the laws of electrostatics. Electric charge exists on the surface of an object. If you can move that charge, cause it to flow along the surface, you now have electricity. And electrodynamics is just the idea of studying or learning about that. What we call current, or what we call electricity, otherwise electric current, is the flow of loosely bound orbital electrons across a conductor when a potential difference is applied. We learned what a potential difference was earlier, a difference in charge. So now imagine like a wire made of atoms, and there's a positive charge on one end and a negative charge on the other, and a potential difference, a difference in charge from one end of the wire to the other, okay? Electrons will flow along the conductor toward the positive charge because they're attracted towards an opposite charge, right? The law of electrostatics says opposite charges attract. So current is the flow of loosely bound orbiting electrons when a potential difference or voltage is applied to the conductor. Conductivity is just a material's ability to transmit electric current. If a material has good or high conductivity, we call it a conductor. It's a material through which, or to more accurately state it, along the surface of which electrons can flow. So it's sort of like, you can picture it like this. I think it's okay. In this picture, you see three cartoon drawings of atoms, okay, three atoms. And as we put an electric force, some voltage, to one end or the other, the electrons are either repelled from a negative charge or attracted towards a positive charge. Those two ways to say the same thing. But either way, the electrons that orbit around atoms are pushed and they hop from one atom to the next. So it says, although we usually think of electric current as a steady flow of electrons, if you get a fine enough grained, zoom down far enough, right, what it really is a leapfrogging of electrons at the atomic level from one atom to the next along the surface of the conductor. So that's what electric current is. That's what electricity is. It's the flow of electrons through the conducting wires to any device. The electromotive force can charge my battery on my computer, right? Can power my microphone, can turn the lights on in the room, spin a motor, generate an X-ray beam. All of the things that we use electricity for, this electric current can be applied to. All right, so let's talk a little bit about conductivity, right? Conductors or dielectrics, right? Things that do conduct electricity, things that don't conduct electricity. And I'm going to key in on one word they said here, right? So it says, usually we think of electric current as a steady flow of electrons, but then they say, at the atomic level, this is important, loosely bound electrons in the outermost shells leapfrog from one atom to the next. The key term there was loosely bound electrons. Materials that can conduct electricity have loosely bound electrons in the outermost shells. Those are conductors. Materials that do not conduct electricity have tightly bound electrons in their outermost shells. They don't want to. This is why, dry wood doesn't conduct electricity, because the atoms that it's made of just like to hold on to their electrons and don't like to let them hop around, okay? So, doesn't conduct electricity. Same thing with rubber. So let's look. Conductors. allows electricity to pass through easily. You just learned that's because they have loosely bound electrons. Copper, silver, aluminum. Okay. Brass and water are all conductors. And you're about 80% water. So you're a pretty good conductor of electricity. Okay. All of your water has nice loosely bound electrons on it, and you can be electrified or electrocuted. You conduct electricity very well. This is why, like, no toasters in the bathtub, right? Conducts electricity. Okay, good. Insulators, also known as dielectrics, resist the flow of electricity because you just learned why, right? Because they have tightly bound electrons. Whatever they're made of have tightly bound electrons orbiting around them. Rubber, glass, plastics, dry wood. So there's your two basic categories: things that conduct electricity good and things that do not. We use the dielectrics to insulate conductors. You put something around a conductor that doesn't move electricity, then cool, you've now isolated the electric current. Semiconductors are a classification kind of in between. Semiconductors are hugely important in the modern technology. Semiconductors are used to make the microchips for our computers. Okay? Semiconductors allow electricity to flow under very specific conditions. Where a copper wire just lets electricity move through it kind of no matter what, a semiconductor says, okay, electricity can flow through me, but only if you apply a very specific voltage, or only if I'm very hot or very cold, or only if you shine a light on me, right? And you'll learn about the light thing later. That's an important one. But semiconductors say, yeah, electricity can flow, but only under very specific circumstances, and then we can use them in our electronic circuitry. Semiconductors, very important in cars and computers and phones and all that stuff. We wouldn't have iPhones or laptops or any of the modern cars if we didn't have semiconductors. Okay. You guys okay there? Conductors, insulators, semiconductors. Okay. Now we're going to talk about electric current and the units that we use to express it. How do we talk about electric current? You already learned about the volt, the unit of force, but now let's talk about the actual current flow itself. Current is the rate of flow of electrons. So electrons per second. If you imagine shrinking down to the wire, standing on the surface of the wire, somehow insulating yourself, but stand on the surface of the wire and count the number of electrons passing by you per second, you could express current in that, number of electrons per second. Or if you stood there for longer, coulombs per hour. Either way, though. Or you can go coulombs per second. Okay? That unit, coulombs per second, is an amp or ampere. So this is the unit that we're actually going to use. Okay? 1 ampere, or amp, or capital A or capital I. So capital A and I get interchanged. I for intensity, A for amp, but they both mean the same thing, is 1 coulomb per second. So if I said 1 amp is flowing through this wire, you now know that if you stood down on the wire, you would count 6.3 times 10 to the 18th electrons, 6 billion electrons moving past you every second. Okay? And you can know, like, it tells you on like computer chargers and stuff what the amperage is. Let's see. So my little transformer here puts through 3.34 amps of current. So it's charging at 3.3 amps roughly. Okay, so that's 3.3 coulombs per second of electrons moving through my wire. Okay, and now I know, that's what's powering and charging my computer, and I know that if I doubled that current, I charge my computer faster. Cut that current in half, I charge my computer slower. Okay, that's like half the. It's 1/3 of the story. Okay, how many electrons are moving along the surface of your conductor? That's amperage. Remember, the coulomb is 6.3 times 10 to the 18th electrons. It's just sitting. Now that you have the ability with voltage to move them, you can count how many are moving past any given point, and that would be your amperage, your current. Is everyone okay with that? Speak now or forever hold your peace. Okay, good, because this, as I said with a few things so far, this is important. We will need this. Amperage, because in the X-ray tube, when we make X-ray settings, when we make the X-ray beam, an X-ray tech always has to set the amperage and you have to set the voltage to make your X-ray beam, okay? We usually don't need an entire amp of current, though. That's a lot. That's a lot of electrons. We need high voltage, as I said earlier, but we don't need high amperage. We need milliamps. Milli is a new prefix for you, maybe. Milli means 1/1000th. Like a meter is like this long, right? But a millimeter is like that long, right? Milli is millimeters, 1/1000th of a meter. A milliamp, 1/1000th of an amp. So now you know, if you've been in the X-ray room, you're setting your MAS, right? Your mass. Part of that mass setting, MAS, is MA, milliamps. Okay? You set your MA. 1/1000th of an amp, or check out the scientific notation, 6.3 times 10 to the 15th. How much smaller is that in the exponent than 1 coulomb? 1 coulomb was 6.3 times 10 to the 18th. 1 milliamp is 6.3 times 10 to the 15th. The exponent got 3 smaller, and 3 times each exponent decrease is 10 times smaller. So go down to, one more time? 1,000 times smaller, right? And or 1/1000th. Okay. So yeah, you had 6.3 times 10 to the 18th is 1 amp. Go down to 6.3 times 10 to the 17th. That'd be a tenth of an amp. Okay. Go down to 6.3 times 10 to the 16th, a hundredth of an amp. 6.3 times 10 to the 15th, a thousandth of an amp, or a milliamp. Okay, we use this one all the time, MA. You need to commit to memory how many electrons are in 1 milliamp. 6.3 times 10 to the 15th. Look at the amount of electricity required to, I don't do what you want with the information, but that much electricity could stop your heart, okay? 0.6 milliamps. So not even 1 milliamp. Less than 1 milliamp is enough amperage to stop your heart. Lock up all your muscles, stop your heart. 0.6 milliamps. In X-ray talk, when we make the X-ray beam, we make an exposure, right? We produce an X-ray beam, kind of like turning on a flashlight. When you turn on a flashlight, you turn it on, and then eventually you turn it off, right? Same thing with the X-ray beam. You set an amount of time it's going to be turned on for. That and your milliamperage setting equals the total number of X-rays produced, or affects the total number of X-rays produced. This is called MAS, or mass. So this mass, MAS, little m, big A, little s, stands for milliamperage seconds, and we get this number by multiplying the milliamperage that we set, multiplied by whatever the time setting is. So let me give you an example. If you had a setting of 100 milliamps on your machine, and you made a 1 second exposure, 100 times 1 would be 100. So you'd be setting 100 mass, right? Let's say you had 100 milliamps and you made a tenth of a second for your exposure. What would you have for mass? 10, yeah, 10 mass, right? Okay. Yeah. Please, yeah. We have just the reason why I'm not doing a bunch on the board is because we're in the principles of exposure module. We're going to do a whole big old thing on this. We're just introducing it, but yeah. So okay, so you have your MA settings and your little s time settings, okay? And then you have what we get from that is something called MAS, all right? So let's say your first MA setting's 100, and you did a 1 second exposure. Okay? 100 times, this is really not doing well. Okay. 100 times 1, sorry, equals 100. So you'd have 100 mass worth of x-rays. Okay? It's like turning on a flashlight and then shutting it off, right? Turn on a flashlight for 1 second, you let out some amount of light, right? Turn the flashlight on for 2 seconds, you would have let out twice the amount of light. Okay, 3 seconds, 3 times the amount of light. Okay, so now I want to set 100 MA again, but instead of this time doing 1 second, I do 1/10 of a second. 100 times 0.1 would be 10. So now check this out. If instead of using 100 for my MA, I decided to use 50. But I made a 2 second exposure. What would the mass be? 100. And what did we say mass was? You can read it if you want. Blue at the bottom. Yeah, equaling the total amount of X-ray exposure. Okay, so when we make an X-ray beam, we set an exposure by making a mass number. Okay, now we don't have to guess, right? Masses change. The amount of exposure needed to X-ray a finger or a hand is different than the amount of exposure needed to X-ray the spine. Okay, you don't have to guess how much exposure for the spine and how much for the hand. You get something in your X-ray room called a technique chart. This is an example of one. I know you can't see what's written on here, but this is an example of one. And I can just go right up to it and go, okay, I'm going to take a cervical spine X-ray. So I come over to cervical spine, and I find the position I want, and then I go over to the mass setting, and it tells me to set 10, right? So 10 mass. So now I just have to figure out my combination of milliamperage and time in seconds that's going to equal the number 10. Okay, when I multiply those two things together. And I gave an example here of how you could get to 10. Okay, so let's say, for example, the body part that I'm going to X-ray called for 100 mass worth of X-rays, 100 mass worth of electricity for our purposes right now. Okay, I can get 100 mass by setting 100 MA on my machine and do that exposure for 1 second, and I get 100 mass, right? But I could also, instead of that, set 50 MA on my machine and make the exposure for 2 seconds and also get 100 mass. So what's the deal between these two? Is there any difference at the end of the line here with the mass setting? No. Okay. So there's no difference. The mass is the mass no matter how I got there, right? Let me give you one more example. I could also set 200 for my MA and 0.5 or 1/2 of a second for my time. And if you're following, that should also equal 100. So these three, 200 for 1/2 of a second, 50 MA for 2 seconds, or 100 MA for 1 second, all come out to be 100 for the mass number, which is the total number of electrons or total amount of electricity used for the X-ray exposure. And if the body part called for 100 mass, if I set any one of the three of these, I'd be fine. Okay?
But does it make a difference if the seconds is like smaller because you're exposing them for a longer time, even if the mass is still the?
You're onto something.
Because
Okay.
it's like you're exposing a body part more.
Yes, but
you don't need to if you're because it's smaller than like doing your spine.
you're onto something. Okay, but I need to clean it up. Okay. So the mass number is the total amount of exposure the patient's receiving. Okay. And if I say that's the total amount of exposure and the mass number is 100 here, 100 here, and 100 here, all of these exposures are identical. Even though this person's getting 2 seconds worth of X-rays, right? And this person's only getting 1 second worth of X-rays. Yeah? They're equal because this person's getting 2 seconds worth of X-rays, but with half of the amount of X-rays being produced at a time. Right? This person's getting 1 second worth of x-rays, but they're getting twice as many or over that 1 second. That make sense? Okay. So these are all the same as far as exposure goes. Okay? But, so here's where you need here's where you like deliberate, right? Which one should I choose? If I can set, like, this is an example of an x-ray control console over here. And I have time setting, or MA settings of 50, 100, 200, and 300 on this machine. Okay? And I've got time settings from 1/60th of a second all the way to 7 seconds. So I have a lot of wiggle room. Okay? I can set my, if this calls for 100 mass, I can set that in a number of different ways. So I've got options. Now, how do I choose what's the best option? Okay? You're onto something. The thing that you're onto is going to become important in radiation safety a little bit. But for our purposes right now, they're all three the same because they have the same mass number. Okay? So which one do I choose? Okay? Now, if a 2-second exposure gives the patient 2 seconds worth of time to maybe wiggle a little bit. Okay? A 1-second exposure gives the patient half that much time to wiggle around. Motion. Okay? And a ½ second exposure gave them even less time to wiggle around. So a shorter exposure, right, equals less possibility for patient motion. And a shorter exposure, even though the exposures are all the same amount of radiation, a shorter exposure will reduce the chance that you'll have a repeated image based on patient movement. Okay? Right, especially for children. So that's one thing. The other side of the coin is, and I won't get to this for until the whole next module, the lower your MA number is, the longer you're giving that dose over. Okay? It's actually better to give an amount of radiation over a longer period of time than a shorter period of time. Okay? Given the same amount of radiation. Okay? So it's we call it protracting. It's better to protract a dose of radiation over long periods of time. Okay? This smaller MA also will allow us to access some geometric improvement in image quality, meaning that we can actually get better image quality at lower milliamperage levels, and that we'll have to do a longer talk later on down the road. So it's better to have lower MA, but lower MA causes you to have longer exposure time. Longer exposure time gives the patient more chance for motion. So you have to decide on, do I want protracted radiation dose with longer exposure times and better image quality, or do I want shorter exposure times, sacrifice a little bit of image quality, and minimize the chance for motion? You have to balance those things. You have to figure out what's the best call under the right circumstances. Okay? I'm making it sound maybe a little complicated right now. This is something that becomes sort of second nature to you as soon as you start to make many, many exposures. You get used to this, right? Which one do I use and when? You usually only have 25, 50, 100, 150, 200, 300. That's 6 different MA stations, 6 different MA settings. You don't have that many options to choose from, so you sort of learn to pick which ones are the best ones for the right circumstances and go that route. But yeah, there's a lot of little considerations here, and in different contexts, these different considerations mean different things. Like if I'm thinking about patient movement, shorter exposure time is better. If I'm thinking about image quality, and I don't have to worry about movement, lower MA is better, longer exposure times. Okay? The point of this right now, though, aside from everything I just said, is that and I like to say it like this: mass is mass is mass. I don't care how you got to the number 100, as long as you got there. Okay, all 3 of these are equal in the amount of exposure. Okay, they all 3 produce 100 MAS worth of X-rays. Okay, so good stuff. We're going to do more on this as we go, but hopefully this gives you and this is just the first time some of you have seen the word mass, right? And now we're learning what it means. Okay, so it's an electrical thing, right? It's an amount of electricity used for an amount of time, and we make that setting on the X-ray control console before every image is produced.
That made a lot more sense. Thank you.
Good. Okay, good. I'm glad. This is really key and crucial to understanding how it works. Okay. Let's talk. So that's important and useful, but now we get to go be less important and useful, because the next time we talk, we got to talk about X-ray machine circuitry, and you guys got to learn what circuit diagrams are and all that fun stuff. So we have to talk a little bit about circuits, electrical circuits now, and so here we go. Okay, electrical circuits A circuit is a circle, okay? In order to have an electrical circuit, there has to be a connection all the way around the circuit. If there's a break in the circuit, the electric current stops flowing, right? If I go over to the wall and flip that switch off, I will have opened the circuit. And what happens if I shut that switch off over on that wall? What will you guess happens? The light, I will open the circuit and the lights in the room will shut off, right? And if I close the circuit by turning the switch on, right? Circuit's closed, electricity will flow, lights in the room will turn on, okay? A circuit is a circle. To have a circuit, conductors must pass from the voltage source through all devices and back to the source. This makes the most sense in like with a battery, right? You plug a battery in and then you turn the device on and it runs, right? It runs until you turn the switch off again. Okay, remote control car, literally the remote for your TV, right? Flashlights, a number of anything that's electrical requires a circuit. If the circuit breaks at any point, electricity stops flowing through the circuit. That's the point of switches, right? Power buttons are just circuit openers or closers, right? Literally, if you've ever gone to the electrical panel at usually like the back of your house or your garage and had to reset your circuit breakers, right? Your circuit breaker broke because you tried to run too much current through the circuit and the breaker's designed to pop open. And then your circuit opens up, the thing shuts off, and you go close that circuit again by flipping your circuit breaker back to on. If you've never looked at your circuit breakers at home, I encourage you to go look at them. If you have an apartment, it's probably hard to do that, but I encourage you to go look at them. If you live with your parents, have them show you. But you can see that they're just a switch, right, that opens the circuit when it's off or closes the circuit to turn it on. Open means off, closed means on. So right now the circuit for these lights in the room, is it closed or open? Closed, meaning because the lights are on. Yeah. Connections being made, circuit's closed. A battery doesn't make electrons. That's what electricity is, right? Electrons flowing. The battery is not making the electrons, and it's not pushing electrons through the wire like a water pushes through a garden hose, right? You turn your water off and let your garden hose empty. You turn the water back on, the water has to get pushed through the whole hose and put the water back in the hose, right? Well, a battery doesn't create electrons. It pushes electrons out from one end and pulls them in from the other, and the wire is the source of the electrons. The battery is the source of the force, but the wire is where the electrons are actually at. The actual conductor is where the electrons are at. This pumping movement fails if the circuit's not complete, and a switch causes a break in the circuit when it's open, reconnects the circuit when it's closed. In order to have an electrical circuit, we're going to need three components. Two are needed. The third one is like, why would you have a circuit unless you had the third one? Okay. But number one, you need something to conduct electricity. A wire is a good thing that conducts any conductor, right? It can conduct electricity. The wire is the source of the electrons. They come out of the battery, but what's powering it's from the battery, but the electrons are in the wire. When you turn your device off and take the battery out, the electrons are still in that wire running through the device. You just put the battery back in or turn it back on, it just begins to push those electrons more. Number two, you need a source of electromotive force. You need something that is charged or something that can produce a charge. In other words, you need a potential difference, voltage. You need something to push the electrons away from the negative charge and pull them towards the positive charge. You need something pushing the electrons through the circuit, or pulling. Pushing and pull, sort of similar thing for our purposes. If you just had that, if you just had a battery and a wire running from this end of the battery to the other end of the battery, you technically have a circuit, right? but what good would it be? Yeah, you just have electrons running through a circuit. You've technically made a circuit useless, right? The point of creating a circuit is to run something, to make some device work for you. And that word work is important. The purpose of having these circuits is to do work. Work is defined as moving things in most cases, but the point is that the work being done does something. It turns a light on. It spins a motor, right? It makes a speaker generate sound. Yeah, it makes my screen put out light. It makes my keyboard work. All that stuff, right? All that is work, or otherwise called devices. Devices to be operated, these act as a resistor. Now, I've given you two things that electric currents have. They have current, which are measured in amperage, and they have a force measured in voltage, okay? There's a third thing here, resistance. And we'll talk about resistance more in a moment, but every device, every light bulb, every motor, everything that gets run by electricity is a resistor. The wire itself is a resistor. A resistor is anything that impedes the flow of electrons. So here's an example of a circuit. You have a battery. You have a wire running from one end of the battery, coming through a device and back to the battery. Now notice there are 3 devices in here. And if I asked you to just trace a line from one end of the battery through one device to back to the battery, you could. And you could do that for each of the devices. To go through this, to go like this light bulb here at the end, notice how if I follow this line, this light bulb at the end here, it's at the end of the row, I could follow the line through, all the way up, through this light bulb and back to the battery, without ever traveling through the other 2 light bulbs. And I can do that for each light bulb. Each light bulb, in effect, has its own pathway. We're going to call this a parallel circuit. Okay? Each light bulb has its own path of electricity. Okay, we'll come back to that in just a second here. As far as resistance goes, every device is a resistor. All motors, flashlight, bulbs, everything that is something that runs on electricity resists electricity. That's how it works. Even the conducting wires offer resistance. They say just as water runs through a hose, the following 3 changes in the conductor increase electrical resistance, primarily through adding friction. A longer wire versus a shorter wire. The longer wire will have more resistance. A narrow wire versus a fat wire. If you think about the wire as having like a surface, right? A smaller wire has less surface area. A larger wire has more surface area. The charge likes to spread out along the surface, right? So with a bigger surface area, you can fit more electrons on the surface, and more of them can move with less resistance. Larger diameter wires, larger diameter conductors are less resistive. Narrower diameter conductors cause more resistance. So why aren't all the wires for our computers like big fat like battery cables if narrower wires cause more resistance? It would have less resistance and it would run better. Less resistance means we'd have to apply less voltage. We could run more amperage through it more easily. It would just run more efficiently with less resistance, and a bigger wire would give us less resistance. So why don't we have giant battery cables for all of our devices?
They don't need as much.
You just don't need it, right? If you think like an engineer, right, you're trying to maximize the function of the device while minimizing materials used, right? And the weight of the components, all of that stuff, right? So all those other things matter, but yeah, you know, the charger running my computer right now could be bigger, the cable could be bigger, and it would run a little better. It would charge a little more efficiently with less resistance and less wasted heat. But There's other considerations as well. So narrower diameter equals more resistance. And then poorly conducting materials are more resistive than better conducting materials. So like gold conducts better than copper. Why don't we use gold for our wires then? What's the obvious answer? It's expensive, right? It's harder to get more of it, right? Copper's pretty abundant. And gold also has some other issues too because it's super malleable. And copper, where you can bend, and it doesn't really break, right? Gold, you bend it a couple of times, right? Like nice pure gold, and then it'll break, right? It's just too malleable. But yeah, so poorer conducting materials though, they add more resistance. So a bad cheap wire versus a good expensive wire, right, will be a bad cheap wire is going to be more resistant and not run as well compared to a similar wire constructed better at a better material. This is why, you know, in I used to play with like car audio a lot, right? And one thing I learned very quickly is that you have to spend the money on the wiring. You'd think like, you know, your speakers and your amplifiers and all that fun stuff that's like the show off stuff is good, right? Good, but if you don't spend the money on the wiring first, you're not gonna get, you're not gonna get the best use out of your equipment. So the wiring becomes important because the wiring adds resistance. Okay, all that aside, moving on. There are roughly two types of general circuit diagrams, circuit layouts. Devices can either be wired in a just a row, a long row, one after the other, all sharing one wire, right? The negative side of one device connects to the positive side of the previous device, and so on, like a little daisy chain down the line, okay? However, like you may have found in older or very cheap nowadays Christmas lights, older is more common, but they don't really do this nowadays. If you have an older row of Christmas lights and one light bulb goes out, if it's wired in series, all of the circuit is broken and all of the lights turn off. And then you're taking your Christmas lights, pulling one bulb out, replacing it with a new one. Nope, that didn't fix it. Put the old bulb back in. Go to the next one in line, pull the bulb out, replace it. Nope, that didn't fix it. Going down the line, all of your hundreds of little, light bulbs in your Christmas lights, holiday lights, excuse me, and checking each one of them, right, until all of a sudden you replace the right one and the whole thing turns back on. Okay, that's a series circuit. That's great. It's easy to build. It's less wiring, less resistance, but it has some downsides that we'll get to. The other option is parallel, and you've seen parallel. I just showed it to you a second ago. Parallel basically says each device is connected and it's in a separate branch, its own pathway, right? You can trace a pathway from one end of the battery through the device back to the battery without traveling through the other devices. I'll tell you in a moment here how that becomes an advantage, but the obvious advantage is if any other circuit breaks, the circuit for the device you care about does not break. So 2 of the light bulbs could go out and the third one would still stay lit. Whereas if in a series circuit, that wouldn't be the case. Okay, so remember the device is a resistor, okay? And there's going to be a relationship between voltage, amperage, and resistance that we're going to get to. But let me just give you an example. The voltage pushes electrons out of one end through the wire in a series circuit to this first device. This first device gets the full voltage and the full amperage, okay? But as we move through this device, the resistance goes up, okay? So coming out the other side, you're going to have less, we'll say less electricity, okay? And so now you got less electricity going to this device, second one. So the bulb runs a little dimmer, okay? And it's a resistant device, so coming out the other side of the device, the electricity is even less now, okay? The third device in line will be the dimmest or running on the least electricity. They don't all get equal amounts of electricity, okay? The first one gets more than the last one. And if any one of these breaks, all 3 go out. With a parallel circuit, there's voltage and amperage running through this device, and it has some resistance, but it makes its way back to the battery. Through a separate circuit, the second device gets its own voltage and its own amperage, and the third device gets its own voltage and its own amperage. The only difference between these three devices is they will all run at the same brightness, but they split the total amperage running through this wire. Okay, whatever the amperage is going through this wire to these three bulbs, it's divided by 3. Each one gets an equal amount of amperage. Where in a series circuit, the first one's your brightest, the second one's dimmer, and the third one's your dimmest. All 3 of these are not that bright, but they're all equal. Okay, and if one of them goes out, the other 2 don't go out. So you can easily identify where the downed light bulb is. And the light bulbs are just an example. It can be anything. Any electric device can be put in place of the light bulb. That's going to bring me now to, we need to talk about another law. You've learned a bunch of laws today, right? You learned Gauss's law. You learned Coulomb's law. You're about to learn a third law, and I think that might be the last law I need to get out to you today, but it's called Ohm's law. Okay? So to do that, we need to talk about the characteristics of electricity. You've learned about the characteristics of magnets. You've learned about the characteristics of electrostatics, electricity just hanging out, right? You've learned about how we electrify things. We've talked about how voltage and current, voltage pushes current, right? Voltage pushes electrons around. And you just now learned about resistance. So we need to put voltage, current, and resistance together to talk about the characteristics of electricity. So here we go. There's 3 things. Current, measured in amps. Electromotive force, otherwise known as potential difference, measured in volts. And resistance is our new one. We measure that in a unit called ohms. Ohms is resistance. To give you an example, 1 ohm of resistance is given by about 1 meter of household wiring. So just wire. 1 meter of wire gives 1 ohm of resistance. Sorry. Let me repeat that. I messed that up. I was thinking 3 feet, 1 meter. It's 3 meters. 1 ohm of resistance from 3 meters of wire, 10 feet. My bad. What's neat is if you have a roll of wire, you can actually check the you can actually learn, if you have a roll of wire and you wanted to know how much wire you had and you didn't want to unroll it, right? You can connect an electrical multimeter device and turn it to the resistance mode, and you can just measure resistance from one end to the other of the wire. And because knowing this, it gives you a readout in ohms of resistance, and you could know how many feet of wire you have in your roll by measuring the resistance. You can do this with a household too. You can, if you knew where the wire started and ended, you can connect, and you can learn how many feet of wire are there too. Kind of neat. Not really useful unless you're an electrician, but it's a useful tool. So 1 ohm of resistance by about 3 feet, 10 meters of household wire. Sorry, 3 meters, 10 feet. Gosh, I'm just not doing well with that. The 3 is like totally short-circuiting my brain. All right, 3 meters. Good. So here's a rule. 1 volt can push, so we want to know like how much is a volt, right? 1 volt can push 1 amp through 1 ohm. That's what a volt is. It's enough. Remember, the volt is the unit of force, okay? So a volt is enough to push 6.3 times 10 to the 18 electrons through 3 feet of household wire. Okay. Voltage, amperage, and resistance in ohms. There's a relationship here. This is called Ohm's law. This is one of the most important laws. Like Gauss's law is great, Coulomb's law is great and important, but Ohm's law, you gotta have it, okay? Ohm's law says voltage is equal to amperage multiplied by resistance. Resistance is in ohms, amperage in amps, voltage in volts. V is voltage, I is amperage, R is resistance. And we'll do a couple, because this is important, we'll do a couple of maybe examples of this. So here's what's cool now. Now you can take and you can, well, with this you'll be able to figure out the amperage and resistance for any household item you have. Okay, so voltage, amperage, resistance, you know what your voltage is for your household items. You'll learn what the wattage is later, and from that you can determine amperage and resistance for any household item you have. You can determine, using this formula, you can determine if how much you can run on any particular electric circuit in your home. This law would let you do a lot of things. Okay, but let's get the law out before we start playing with it. Okay, so that's the law. There's a couple of ways to do this, but most of the time what you're doing here is you're going to be given, at least for our purposes, you're going to be given two parts of the formula. It's 3 parts, right? You're going to be given 2 parts, and you're going to be asked to tell me what the third one is. Okay, that's the trick. That's the calculations you're going to have to do. Okay, for that I like the T-triangle method. Okay, the T-triangle method says cover 1. Okay, let's say cover the V. Right, so let's take my little laser pointer, put it over the V. Okay. That's what I would want to find out. That's what I'm solving for. Okay, I don't know the voltage, but you've told me the amperage and resistance. Now in the triangle, V always goes on top. It doesn't matter if I or R go on the left or right, but V has to go on top for this to work. So I want to know the voltage. Let's cover it. That's my X, my unknown. Okay. With I and R next to each other, things that are next to each other, the rule is going to be multiply. Okay, so if I tell you amperage and resistance, multiply them together, that tells me what the voltage is for the circuit. So I didn't know voltage. I can figure it out by knowing amperage and resistance. Now, if I want to know the resistance, and you give me the voltage and the amperage, I can take, in the rule for things above and below, you divide. So V divided by I. V's on top, I's on the bottom, V divided by I. So if I don't know resistance, give me the voltage and amperage, and I'll tell you the resistance. Voltage divided by amperage is the resistance number. Same thing is true if I want to find out the amperage. I don't know that. You give me voltage and resistance, I'll tell you what the amperage is. So you can remember the T-triangle, or you can just remember these 3 ways to write the formula down. V equals IR, that's the base way it's written down. I equals V divided by R, amperage equals voltage divided by resistance, or resistance equals voltage divided by amperage. Good. So now you've got a way to do this. If you can just remember V equals IR, you can just, the other 2 kind of just are given. But some people like to remember all 3, or the T-triangle. All are fine. They're all the different versions of the exact same thing. So let's use an example here. Let's see if we can figure something out. I mean, that gives you the answer, but let's walk it through. So you're told a light bulb in your house has 30 ohms of resistance and runs on 4 amps of current. So you now know R and you know I, and we don't know V. Okay, V equals IR. Let's come up here. So we don't know V. We can leave it as V or put it as an X if you like, it's fine. But we know amperage is 4 times resistance, 30. 4 times 30, says it right there, 120. 120 what? 120 volts. Now you know what the voltage is for your household device. Another example. A hairdryer gives 14 ohms of resistance. Somebody tells you that. And they tell you the voltage from the plug in your house when it was measured was 112. How many amps of current are flowing through the hairdryer? So V equals IR. Let's just set it up like that. Let's do V equals IR. So what are you given? You're given resistance of how much? 14 ohms. Okay. And you're given voltage, 112. If I just leave V equals IR like it is, I now don't have the I. Okay. So if I left this formula like that and I wanted to be able to solve it, what do I have to do?
Divide by 4 from both sides.
14.
Oh,
Right.
14, okay.
Divide by 4. I was messed up when you write 14. Divide by 14. And I get and then this is a little backwards, but it still works. I get 112 divided by 14 should give me 8. Should be flip-flop, I equals 8, amperage equals 8, right? But the point is that you can quickly and easily, without even monkeying around with the formula, figure out that it's 8 amps of current. You give me 2 things, I'll tell you the third thing. That's how formulas should work. So now, I mean, in principle, we could put any random number there for 2 of the 3 things, and you can give me the third one, okay? How do you guys feel about that? Anybody have any questions? No, I think that one's about as straightforward as it can be for formulas. Let's do one third one. I won't write much down here, but let's see. This time you have a toaster. Toaster runs on 7.5 amps. The voltage is 115 volts at the time, and so we just want to know resistance, right? So E equals IR. What do we know? We know the voltage is 115, and we know amperage. So now we're trying to find resistance, right? So what do we need to do? Let's do V equals I R. T triangle, okay? So we need to find out what? Resistance. So we put our finger over that or block that out, and it's V divided by I, okay? Voltage, 115, divided by amperage, 115 divided by 7.5, I'm trusting the math here, 15.33 ohms should be our answer. Okay.
So you said test-wise we won't have to calculate anything, or will we?
Now, Ohm's law, I might give you something, okay?
Because in the homework, I think there was one that said kilovolts.
Yeah.
Do we have to change it to volts?
Yeah, so kilovolts is just 1,000 volts, right? So they
Okay.
say 10 kilovolts, it's just 10,000 volts, right? So yeah, you would need to change it into voltage to make it work for you. Yeah. Okay.
You have to round up.
One more time.
You have to round up, so if it's like 15.3, like if you ever get.
Was it 15.32 recurrent or something when you did it?
No, I was just.
Oh, okay.
I just,
Well, yes, you would round up.
okay.
I wouldn't go further than the second place after the decimal point, like to the 100th position, right? I wouldn't go 1,000th or on. Let me just double check what the actual, like, it comes up on the calculator.
15.33333.
Three recurrent. Okay, so then you can just cut it off. You can honestly cut it off after the tenths, right? But don't write the recurrent, you know.
Well, yeah, no.
Right.
Like,
But
it was like
and you
15.3.
never really need to go past the 100th place. Yeah, and if it is like, if it was 15.328 like that or something like that, 15.328, you would round up to 15.33. Yeah. So, yes, you can round up. Yeah. Okay. Let's see how far we can get. Yeah, 'cause I know I'm going to do, all right, let's do power, and then we'll probably call it good for today, and then we'll talk about waveforms next time, because waveforms take longer. All right, so we talked about circuitry, right? We talked about characteristics of electricity, and I gave you Ohm's law, which talks about voltage, amperage, and resistance, which are like the 3 parts of the electric current of electricity, right? There's something pushing the electricity, there's the electricity, the current, and there's something resisting the flow of electricity, right? All 3 things, we learned Ohm's law for that. The power formula, or the power equation, is just a way of just expressing the total amount of power, right? And you have current flowing through a wire, and something's pushing it. The amount of current and the amount of push matter, okay? The voltage and the amperage matter. So the power formula is just a way of expressing that. So let's read a couple things. Power, in general, is defined at the rate at which work is done. As a simple example, not an electrical example, 2 cars reaching the top of the hill do the same amount of work, but the one with the more powerful engine gets there quicker, right? A Volkswagen Bug and a Dodge Charger try to climb a hill, right? They might both get to the top of the hill, but the Volkswagen Bug is probably going to get there last, right? They both did the same amount of work. They both got to the top of the hill, but one's going to get there quicker because it can do more work more quickly. That means more power. Okay, the one with more power gets there quicker. That's the idea there. Work is equivalent to energy spent, right? That big motor in that Dodge Charger would spend a lot more energy more quickly, right? So work is equivalent to energy spent. Power is the rate at which energy is used. So the formula looks like power is equivalent to energy divided by time. That's all we're going to say there. Really, I think what's more important here is that you remember this. Work is equivalent to energy spent, right? You want to do more quickly, that's going to require more energy, okay? Think about it like with your car. Just another car example, right? You got here today. It took you some amount of gas to get here. If you wanted to get here much faster in that same car, you would have had to put out the same amount of distance, right? Same amount of work to get here, same distance that you drive, right? From your home to here. But if you want to get here very quickly, you speed and you get worse gas mileage. It cost you more money to get here. You had to use more gasoline, more energy to get here. If you just drove the speed limit and planned better for time, it would take you more time, but you would have used less energy, saved more money on gas, right? Okay, good. So power is equivalent to energy divided by time. That's all we need for that. The total power of any given system may be thought of as its quantity, how much force, times the quality. How strong is the force? So in electrical terms, quantity would be the current, how many amps. And quality, strength, is how many volts. So our unit for electrical power is going to be talking about volts times amps, or intensity times force. Let's see what they say here. With a given amount of power, one can move several cars slowly or a few cars quickly. Same thing as it's this exact same idea as I said, like, take your car, drive fast to get here. You're going to get here faster, but you're going to use more gas getting here. Drive slower, you'll use less gas. Same idea. Within an X-ray beam, the total power is represented by the intensity of the X-rays, current, amperage, times the voltage or energy that they carry. You can make an X-ray beam with very low voltage for a very long time, or make an X-ray beam with very high voltage for a very short amount of time, and they may have an equivalent amount of total power, total energy used. We have to not only consider the milliamperage we're setting and the time that we're setting, but also the voltage setting that we're making. For electricity, total power is the quantity of electrons times the energy with which they are being pushed. So amperage times voltage. And the unit we use is called the watt. Go home, unscrew a light bulb, look at what it says, right? It's going to express, your light bulbs always give you the power, right? The light bulbs usually don't tell you, here's how many amps I'm drawing and here's how much voltage we're using, right? The light bulbs just tell you, here's my wattage. I'm a 60 watt light bulb, right? Or I'm a 10 watt light bulb, whatever, right? And if you've ever gotten these, right, that a 60 watt and let's say, 70 or 80 watt light bulb, whatever, the 70, 80 watt light bulb is going to be brighter, right? It's going to use more power. It's going to be brighter. It might even be a different color, okay? The watt is the unit of electric power. Something that has a higher wattage uses more power. The rate at which electricity is used, right? You get your electric bill measured in kilowatt hour. Oh, kilowatt is 1,000 watts. You get your electricity bill measured in kilowatt hours. How many kilowatts did you use? How many kilowatt hours did you use? A kilowatt hour is just 1,000 watts used for an hour. How many of those did you use? How much electricity total did you use? The rate times the time to get the total consumption. This formula is similar to Ohm's law, so please don't confuse it. the total amount of power given in watts is equal to the amperage times the voltage. All right. So you know a couple things about your home, okay? For one, house is running 110 volts, okay? Except for the very special parts of your home, like your electric dryers that run on 220. Ignore that. Home's running 110 volts in the United States and elsewhere. And let's say I give you a 60-watt light bulb. Okay, that's the power, total power used by the light bulb. And I ask you to tell me what is the amperage that that light bulb is, that the light bulb uses. So how much current does the bulb use? Okay, so from what I showed you here, I told you, I don't even need to tell you because it's just a known thing and you should just remember it. Homes run on 110 volts. By the way, it's 110 to 120 because voltage fluctuates a little bit, but homes run on 100, it's just called 110 to make it easy. Homes run on 110 volts, so you know what the voltage is. You know what the total power used by your light bulb that you're going to screw in is, and I'm asking you to figure out the amperage. So, P equals IV. We want to figure out amperage. Okay? So, to figure it out, to make this formula work correctly, we're going to put amperage over here, and then we would be dividing the total power by the voltage, right? Power divided by voltage. Notice in the T triangle, P is on top, V is on the bottom. So you would set up the formula like that, and then you just plug in your numbers. So I'm going over here now. Amperage equals total power is 60 watts divided by 110 volts. And you guys can plug that in and tell me what you get.
It's 1.67.
Should be a number smaller than 1.
Wait. Oh, I did it
Backwards.
0.54. Oh, I guess if it's 0.55 because you round up.
Sounds good to me. The intensity or amperage is 1/2, right? Your little 60-watt light bulb uses 1/2 an amp, roughly, 0.55 amps. So there's your answer. All right, so you can go home, you can look at your light bulbs in your house, and you can see what their amperage draw is. Here's the deal. Just for like your homes, the voltage is equal, okay? So the amount of amperage that your light bulbs draw, that determines the total amount of power used, okay? Do you guys anyone have LED bulbs at home? Go home, check out your lights, check if they're LED. If they're not, switch them to LED. LED light bulbs, while they put out, like let's say a 60-watt incandescent light bulb, right? And LED bulb that matches that brightness. An LED bulb that matches the brightness of a 60-watt light bulb might only pull like 4 watts of power, okay? They use way less amperage, okay? The LED bulbs consume less total power. They run at the same voltage as your incandescent bulbs or your fluorescent bulbs, but they use so much less current that they are using so much less power, and they will save you money on your electric bill, okay? So you can go and check your light bulbs and see what's not running on LED, switch stuff out, and you will begin to instantly save some money on your electricity because among other things, lights are a big, draw of electric current, and now you will have freed up that electric current to either not use it at all or be used on other things in your home, right? The power can be used elsewhere. There's only a certain amount of power your home can pull. Your home can typically only draw down about 100 amps total, and so like in the summertime when you're running your AC, all this other stuff to cool things down, you're using your freezer a lot to cool your popsicles down and stuff, the LED bulbs are going to save you a little bit, okay? All right, so so you can figure out now if you're given the wattage and the voltage is a known unit, right, like in your homes, you can now figure out what your amperage draw is, and that will give you an idea of your total power used. Okay. And they give an example. Let's just look at their example here. So you're given a 40-watt light bulb plugged into a 120-volt socket. How many current? What's the current in amps? And the story is going to be the same, right? You're told the wattage. You're told the voltage. Voltage divided by wattage divided by voltage. And then in this case, we're only using a third of an amp. Notice how a third of an amp versus 0.55 amps, we're using less power here than that, right? Even though that one has 120 volts going to it, because the wattage is so much less, okay? Okay. And let's see where we're at. Yeah. So for today, because I'm going to need to get into waveforms next time, so that takes a long talk. So for today, we're going to stop.